Okay, so arc lengths in space. So we're just, we just have a couple formulas we basically apply to certain things. There's the position functions, generally speaking, like this, and it has the lengths of its smooth curve. If you have a position function like this, which is the standard one, I, j, k with x, y, and z, respectively, you have the magnitude of the vector v's integral of just that between, definite integral, of course, of it is the lengths between those 2 points, b and a to b. That's just how it technical, like that's what v is, magnitude, because v is that. It's v is the derivative of r. Pretty much is one way of putting it. The unit tangent vector is just v divided by the magnitude of v. And arc length parameter is base point p at t0. It's basically very similar, but it's just with, in general, it's the integral of v, but it's the magnitude of v, but it's with t, and you'll see that with one or two examples. Find the curve's unit tangent vector for three types of position functions, for three different ones. Then we have to find the lengths that indicate a portion of the curve, which is going to be L then. First, just finding the unit tangent vector. So for this one, 2 cosine t I plus 2 sine tj plus square root of 5 tk, and 0 is less than or equal to t. It's between 0 and pi t. Those are going to be a. That's going to be b and a. I mean a and b. 0 b. That's for when we do the formula, when the integration things. The first thing's not integration, it's derivatives, and other types of things used to find the unit tangent vector. So the derivative of RT will give us V at t, which is each component its own derivative. Square root of 5t is square root of 5. That's a constant times a variable to 1 power. 2 cosine t becomes negative 2 sine t, and 2 sine t becomes 2 cosine t. And the magnitude of this is, it becomes 4 sine squared t plus 4 cosine squared t plus 5, and it's 4 times the sum of sine squared t and cosine squared t plus 5. And this is 1, because of sine squared plus cosine squared equal to 1. When you have that with just a single variable, and it's like, so 4 times 1 plus 5, that's what the square root is. This whole thing just becomes that, and then it's 4 plus 5, which is equal to square root of 9. Then it's 3. So in the end, that's all it is 3, and then you basically do division of the vector by 3, which is division by the magnitude vector components. And you pretty much have, you can also write this as negative 2/3 sine t plus 2/3 cosine t, but it's negative 2 sine t over 3 plus 2 cosine t over 3 with the respective component, and square root of 5 over 3, the component. That's your unit tangent vector. And L is equal to the integral of 3 basically for buying 0, and that's just 3t. T to the 0 power is technically 1, anything to the 0 power is 1. So t to the 1 divided by 1 would be just t. That's, as you've seen before, integration works like that. The general formula works. Because you could just ignore 3, technically bring it out if you really want to be technical. That's like a tiny step that you can, is usually omitted. So basically integrating 1 basically is what the point is. And you're multiplying that by 3. But anyway, pi and 0, 3 pi minus 3 times 0 equals 3 pi. And that's your lengths of indicated portion on the curve. That's how you find it. This one's more interesting because integral is not as quick. I mean, it is quick for overall compared to a lot of integrals out there, but this one's a little bit, they have one extra step involved with taking an integral before you can take it. But yeah, you have position function that looks somewhat simpler. Ti plus 2/3 t to the 3/2 power k. 0 to 8, it's that's the range, is what you want for t to be. So the v is just I plus t to 1/2 k, or I plus square root of tk. T to 1/2 power and square root of t are the same, because 1/2 raised to 1/2 power means square root. But yeah, basically the square root of t is just 1, and the square root of 2/3 t to the 3/2. 2/3 is a constant. So you do the square root of t to the 3/2, and that's, you drop down the 3/2, multiply that times it, and then you have t to the 1/2 because that's subtracted by 1. And it becomes just 1 times t to the 1/2. But that's simple. I'm sure you at least would be familiar with derivatives, very familiar by this point in a calc career. 3 courses in. Was that simple one? V, the magnitude is just 1 squared plus t to the square root of t squared, basically. Or it's 1/2, but putting that square root even makes it simple, makes it more obvious. It's 1 plus t underneath the square root. That's what the magnitude is. That's all we can do, simplify it down to. There's no tricks to simplify it any further. So the unit tangent vector is just v divided by the magnitude of v. So you get 1 over square root of 1 plus ti plus square root of 2 divided by square root of 1 plus tk. And that's 1/2 the power. Now we have to find L. This is the integral of square root of 1 plus t, which is 1 plus t to the 1/2 power. So we can use that power rule, but we can't use the integral sim without making it a little bit simpler. We make u substitution for this, and I mean, it's fairly obvious that we're not going to be able to cancel out. And I'll show you real quick a review of this. A lot of times you cancel out stuff with u substitution and make it simple that way as well. But this time, it's 1 plus t is what we let the inside of this, which is one of the more common ways. Something raised to a power, you make u the inside. Is one of the things to always try out before you do anything else. Always trying to so derivative of u equals 1 plus t, derivative of u and is du equals 1 times dt. Derivative of this both sides, and it's du equals dt essentially. So you substitute u in, and you substitute, there should be du here for dt because du is equal to dt. And then I set t equals 0 and t equals 8 into the u formula to get 1 and 9 for the integral ends. So, and in the end, u to the 1/2 will be u to the 1/2 plus 1 divided by 1/2 plus 1. So it becomes u to the 3/2 divided by 3/2. It becomes 2/3 because you flip the fraction when you divide by a fraction. And 2/3 times u to the 3/2 power. You integrate from here, and it goes through like normal. L equals 52/3. Real quick review on u substitution that you get in Calc 1. Really good. You have to do quite a few examples of it. But u equals, for this expression I made u equal 1 plus t fourths. So du is equal to 4t cubed plus 0 technically, but we don't draw that. Because adding 0 to something is literally doing nothing to the problem, to the expression. And that's dt, so dt you basically divide 4t cubed by both sides, and you get dt equals du over 4t cubed. And you put that in, essentially substitute in. Technically not it's a little bit more complicated than what's technically going on. But for our purposes, you're basically substituting in it. And t cubed will cancel. They'll leave you u cubed times du over 4 basically, and then you take out 1/4 out to make it just simply the integral of u cubed du, which we have that basic formula for, where it's just u to the 4th divided by 4, something cubed, integral 3 plus 1 divided by 3 plus 1. So you have u to 3 plus 1 power divided by 3 plus 1. So u to the 4th by 4, and t equals 1 and t equals 0 integrals. Put t equals here to emphasize that we have to do something about that. So we either put it back into terms of t. U equals 1 plus t fourth, so this should be 1 plus t to the 4th, all to the 4th power. I did not write that clearly, but it doesn't change that. And in the end, you get 15/16 by doing this, following through my detailed work. This is one method, and method 2 is why I did in the other problem, and I think is more efficient, at the very least. This way you don't forget to substitute back in u. Do this early on. Get t in terms of u. So t equals 1 and t equals 0, I get my values of u equals 1 plus 1 and u to the fourth power, and u equals 1 plus 0 to the fourth power is equal to 1 plus 1 and 1 plus 0, so 2 and 1 respectively. I get two values. And you plug that in, you get the same answer, 15/16 for both methods. And, you know, some professors might prefer this method while others might prefer that, but they're both valid. You know, a professor might show you more on either this more example whenever you do class problems or something with it, or they might use this method more. It just really depends. My calculus professor, calculus 1 professor, never really used this method. They just substituted back in. But this is a valid method as well. But yeah, so just that's an overview of it. And now let's go back to the scheduled program. RT equals cosine cube t j. It's j plus sine cube t of k. So, and 0 between 0 and pi halves. So the vector, the v is equal to, so we're using, we're basically having to do, I think you call it the chain rule technically, because you have cosine cube t. This is technically, I try to show it, that's cosine cube t, the derivative of that is equal to the derivative of cosine t all to the cube power. And what technically doing the chain rule, we drop that down and it's 3 times cosine squared t times negative sine t, is shown here. Same thing with that one. Sine cube t is sine t cubed. Common thing the expression has. And that's what I'm showing in red here is the exact way to get these. We have cosine 3 times cosine squared t cosine t. So we negative 3 cosine squared t sine t, and you know j plus 3 times sine squared t cosine t. Okay. Magnitude of this vector now, since we need that, is all that squared, most of these, and you get 9 cosine to the fourth power t times sine squared t plus 9 sine to the fourth power t cosine squared t. And in the end, it's you can divide out cosine squared and sine squared t as well as 9. You can distribute it out and get that multiplied by cosine squared t plus sine squared t. And that's equal to 1 as sine squared plus cosine squared equals 1. And it becomes just the square root of 9 cosine squared t sine squared t. And that can conveniently be all gone out, taken the square root of individually, so it's 3 cosine t and sine t, since they're all product of each other. And it cancels out the square root. And then you take this, and a lot of things get canceled out when you do the division of v and magnitude of v, as I try to show here. Those things crossed out. And you get negative cosine tj plus sine tk. And that's your unit tangent vector. And now it's time for L. Since we want to also find the length of its smooth curve. The length of the smooth curve of this function is the integral of the magnitude of v, which is 3 cosine t sine t, between pi halves and 0. Okay. We have to use some trig identity type of work, as well as u substitution. The u substitution is very minor, and it's something that seems like you could just memorize, but it's better just to do the classic way of u substitution. I mean, there are like tables of integrals with hundreds of integrals that exist, and even calc books still have like 100-some integrals of specific types, like common types. But it's, you know, it's whenever it's possible, you should try to use like u substitution, because I feel like that's part of it. The u substitution, saying like some of those formulas are no one memorizes everything. I think u substitution, in my opinion, was developed as kind of a way, you know, like that same teaching and making sure it's taught early on is to make sure people don't have to memorize integrals, at least the more common ones. You see, I mean, there are still some integrals I think you basically do have to memorize pretty much in other courses, but let's try to keep things simple and just use u when it works. But besides that, basically, first step is to use a trigger. Basically, okay, we have to fit it. do have to do like every trick in the book basically to solve this integral, because it's the product of cosine and sine, which is never good. It's never easy to solve when you have cosine and sine multiplied together. That's basically it. So we can write this as 3 times 2 over 2, because that's basically 3 times 1, and a number can be written as a product of 1. So 2 over 2 is 1. So, and we do this because we want to make it 2 cosine t sine t, which is why I put here. So we can draw out 3/2 outside the integral. And 2 cosine t sine t is equal to sine 2t. So that's what we have. And that's all about sine 2t dt is what we integrate. U equals 2t means that du equals 2 dt, so dt equals du over 2. Plugs it in, and for t equals pi halves we have u equals 2 times pi halves equals pi, and t equals 0, that's u equals 0. So pi and 0, we have 3/2 times the integral of pi 0 pi integrand the integrand sine u du over 2. This is 3/2 times 1/2 times the integral of sine u du, and sine u du will just be negative cosine u, because that's how it works. Yeah, because it's just the exact opposite of derivative. So like the derivative of negative cosine of something would be positive sine. That's why. So pi and 0 and plug in 3/4 times it. So 3/4 times negative cosine pi minus negative cosine 0, it becomes negative 1 plus 1, or negative 1, I mean, because cosine of pi is negative 1, negative of that is positive 1. So it becomes basically 3/4 times 2 if you solve the work. But that becomes 3 times 2 over 4, which becomes 3/2. So L equals 3/2. And that problem works. So now for these last 2 examples, we want to find the arc length parameter along the curve from the point where t equals 0 and find the length of the I think L is the one that you have to worry about really for t and L. Those two are the 3. I don't think you have to worry about this technical S to t equals, between t0 t. I don't think that's an interesting thing sometimes, depending on the course. If you're not really going over it in class, it's probably not necessary, but it's good to look at real quick since it's short. The main part is to find the lengths for these. In that indicated portion, 0 and pi. So 4 cosine t plus 4 sine t plus 3t with I, j, k respectively. V is equal to negative 4 sine t plus 4 cosine t plus 3k. And then you have, so V is equal to just take the derivative of each part. So 3k, you have 4 cosine tj, negative 4 sine ti, like I bought. Then the magnitude is like before, you've seen this. We've seen I think one just like this, but basically we distribute, so we have sine t squared plus, sine squared t plus cosine squared t, and then it becomes 1, so you have square root 25, it's equal to 5. And that's your magnitude v. You can go through the process, just show it. And then S of t is equal to 0 to t. Do you want that in this thing? Yeah, because it's where t equals 0. But it's equal to the integral of 5 dtor, I guess technically. So it's 5 tor, it should be, pretty sure. T and 0, so it's 5t minus 5 times 0, which equals 5t. And that's technically the arc length parameter. But not much to worry about. It sort of is kind of like if you took it in general and you found like the integral was no bounds and you found, I think, c, you'd basically solve for c and you'd get this as well. That's basically what's going on, solve for c at t equals 0, then you get your expression of 5t total. But this method works. Go ahead. And now L is very similar. It's going to be 5 dt. It becomes 5t pi half 0. And it doesn't have t involved though. So it's 5 pi over pi halves. Yeah. L equals 5 pi halves. One last bomb. The position vector of et cosine ti plus et e to the t power sine t j plus e to the t k. Okay, now we're using this type of stuff, and we have negative ln 4 to 0. This is what t is in. For lengths, no, the lengths of the individual portion of the curve, like L. Basically. No. Okay, so for the first part, product rule is used. These are e to the t power times cosine t. We can't do it. We have to use product rule, which is the sum of these two guys. Same with that one. The derivative of e to the t is e to the t. Like e to the x is e to the x. Simple and done. So first part, it's e to the t times cosine t. So that's the derivative of e to the t. And then it's plus negative et, because it's times the derivative of cosine t, which is negative, it's negative sine t, so it becomes negative et sine t. Same thing here, idea e to the t is derivative of e to the t, so et sine t plus et cosine t. Yeah, I think that's clear. And simplifying it down, And then the magnitude is not going to be pretty of vector v, but you sometimes have to go through this as an exercise at least to make sure you can, yeah, look at this. So it's get this in your mind. Yeah, the v, I think we should do like this. So we have all this expression, so of course. Now something raised to power with already power will be, e to the t squared is e squared t, e to t, e to the t power. That's how exponents works. So multiplying these multiplication, you get a lot of things cancel out. I hope you can read what's going on, but I'm not going to try to explain this word for word. But pretty much you do the multiplication of you're squaring a binomial, two terms, adding or subtracting them. You're basically having to multiply. You technically get 4. Yeah, I have 4 right here. I showed it for once, all 4 of them. For each of these plus e to t, so 9 terms. And 4 of the 9 terms cancel out. And you're left with, I kind of skipped out a little, well, not fully. But I wanted to do this. So when you cross those out, you see e to the 2t times cosine squared t minus e to the 2t, plus e to the 2t sine t squared t. And you have another one, e to the 2t sine squared t plus e to the 2 cosine. So you have these. So I factored out e to the t from both of those individually. This, as well as, these two and these two. So it's cosine squared t plus cosine squared t, and then another one. And those are all equal to 1. So you have e to the 2t times 1 plus e to the 2t times 1 plus e to the 2t. You end up with 3e to the 2t power. And in the end, that's technically, et squared, so you can just divide that. So et times square root of 3, or square root of 3 times et is that's what the magnitude of v is. Got that? Now finally we can get somewhere. We have a magnitude of v at t. Check this one, via Torah t and 0, so we integrate square root of 3 et dt, d Torah here. Length parameter process. It's just e to the t, and the integral of e to the Torah is just e to the Torah. Technically you could, there's a process to it, but for this one we're not going to worry exactly about that. Usually, the integral works out. When it's just a simple number like that, the integral is not any harder than the derivative for just a normal thing like that. for these cases. The point is that you evaluate that between t and 0, so you have square root of 3 times e to the t minus, we're going to be technically e to the t minus e0. So it's square root of 3 times e to the t power minus 1, because e to the 0 is 1. Anything to the 0 power is 1. And that means that it's square root of 3 distributed, and it's square root of 3 times et minus square root of 3 is what our arc length parameter is. Then the lengths. L equals between 0 and negative length 4. It's basically square root of 3 et, same thing as before, same integral, so it's just e to the t power. So e0 minus e to negative ln 4 times square root of 3. Keep that square root of 3 out till the end. E to the 0 is 1. This is technically wrote in that. You can write it this way. I'm doing it. Minus 1 divided by e to the ln 4 power. And that's 1 minus 1 to 4 because e to the ln 4 is 4. So that's square root of 3 minus square root of 3 divided by 4. Because I distributed it in at that point. And that's 4 square root of 3 divided by 4 because I multiply square root of 3 by 4 over 4. Like multiplying over 1. So then I just subtract. They have the same denominator. So it's square root of 3 times square root of 3 divided by 4. That's your lengths. And that's it for that section. Just a couple examples like that. They take forever to talk about.